You are watching this video on YouTube right now because your mobile phone has a processor in it. Without that processor, it won't be possible to even watch a video on YouTube, let alone do some calculation. For example, you can use the calculator app on your phone or on your computer to, let's say, add some numbers. So, behind each and every operation that you perform using your mobile phone or your computer, there is a processor. Now, the processor itself is actually built up of small components that are called logic gates. Okay, so logic gates are like the building blocks behind all the processing that happens inside the processor. Okay, so think of any kind of thing that you are doing, including me recording this lecture right now for it to be posted on YouTube. Even this requires some intervention by the processor, and the processor is actually just built up of these logic gates. So logic gates are like the building blocks of a processor. So understanding how these logic gates work is key to understanding how the processor work, because if we understand how the processor work in general, that's a main thing that is the focus of our study in computer science, right? So I hope the idea of logic gate is clear to you. Logic gates are like the building blocks of your processor. Okay, that is there in your tablet, phone, or computer for that regard. Okay, now there are 6 kind of logic gates that we are going to study in this topic. Okay, so I'm going to review each one of those logic gates in this video. For now, I'm just going to introduce them. In the next video, we will talk about how those logic gates combine to do some sort of meaningful job for the processor. Okay, so let's understand this. The first type of logic gate that we have is called the AND gate. Okay, and the AND gate, as we understand already that computer only works on bits, ones and zeros, the AND gate has 2 wires that takes in the signal. AND gate processes those 2 signals and produces one output. The logic of AND gates goes as follows. If, as you can see over here, I'm showing the different inputs that A and B can get. The reason why I have 4 rows over here is because there are 4 possible combination of signals that these 2 wires can get. Okay, so one of them could be 1 1, one of them could be 1 and 0, one of them could be 0 and 1, and one of them could be 0 and 0, right? So there are different possible signals that A and B can get, and we are trying to understand over here what outputs would AND gate perform. Well, the output for AND gate is fixed based on its logic. The AND gate only gives out a 1 when both of its inputs are 1. Otherwise, it always gives out a 0. Okay, let me record that logic over here. Gives 1 only when both inputs are 1. All right, there is this diagram that you need to know for an AND gate, but in addition to this diagram, you should also know how to mathematically represent it. One way of representing it is by writing down A and B. That's not too complicated to understand. You basically have the 2 inputs, right? And in between, I've written down the gate, which is the AND gate. There is another more compact way of representing it, which is A times B. Okay, so that's another way of representing the AND gate. A times B, which is literally this dot over here, is basically representing the multiplication operation, and it's easy to understand, at least over here, why that multiplication operation applies, because only when you have 1 times 1 you get 1. Otherwise, even if there is 1 0, you should be getting a 0 as your output. Hence, this is AND gate is basically following the logic of your standard multiplication operation. Okay, the second type of gate that we have is called the OR gate, right? Now the OR gate follows the logic that even if one of the input is 1, then it's going to give out a 1, otherwise it gives out a 0. Okay, so let me write down the logic. It gives 1 when even one of the input is 1. Okay, so it gives out a 1 when even one of the input is 1, otherwise it gives out a 0, which means only in the case when both inputs are 0 will it give out a 0, otherwise it will give out a 1 in the rest of the cases. So you need to really kind of memorize over here the exact output that you will get given that you have a particular gate provided to you in the question. Okay, just like AND gate, we will also try to represent this mathematically. So the way we represent OR gate is A or B, right? Again, that's quite straightforward to follow, but the more compact way of representing it is by writing down A plus B. All right, that's another way of representing OR gate. Now the third gate that we have, it's called the NOR gate. Okay, what's NOR gate? Well, NOR gate basically takes the OR gate and flips the output of the OR gate. Okay, so let's just look back at OR gate over here. Let's look back at OR gate in the same frame. So let's look at each of the outputs of OR gate in each case. Okay, so for 1 1 1 for 1 1 it gives 1, for 1 0 it gives 1, for 0 1 it gives 1, and on 0 0 it gives a 0, right? So if you were to have the exact opposite output, which is the case of NOR gate, so it gives opposite of OR gate, right? So if we are, what it gives out is just the exact opposite result of OR gate. That means that it is going to give you 0 in all cases except the last one. Okay, so if you remember the OR gate, you automatically also remember the NOR gate. All right, again, there is a mathematical way of representing it as well, which is A or B, and then not in front of it. What this not really represents is it's basically saying that you apply the OR gate, but then you take the opposite of it, right? Again, there's a compact way of representing this as well, which is to do A plus B, but then you put a basically bracket on top. Okay, you may also find another alternative representation in which we do A plus B, but then we add a dash over here. Okay, so it's either this or that. You can follow whichever one makes sense to you. All right, the fourth type of gate that we have is called the NAND gate. Okay, in NAND gate, again, just like the NOR gate is the opposite of OR gate, NAND gate is the opposite of AND gate. Okay, and remember, in AND gate, let's look back at the logic of AND gate. The way it works is it gives out a 1 only when both inputs are 1, otherwise it gives out a 0. So we will flip that around and say the NAND gate will give out a 1 when you have even one of the inputs as 0, and it gives out a 0 when both inputs are 1. Okay, so again, if you have memorized the logic of AND gate, just flip it around, and then there you get the logic of NAND gate. Okay, so X, the way you represent this mathematically is A and B, right? Sorry, A and B, and then you put a NOT in front of it. Okay, then you have the more compact way of representing, which is A and B, and then a bracket on top of it. Just like OR gate, we have an alternative way of representing the same thing, which is A dot B and then a dash. So again, remember, it's going to be either this one or this one. You can use whichever one you like. It's up to you, but there are these two ways of representing the same thing. Okay. The fifth type of gate we have is called the NOT gate, and you have been kind of already introduced to it. The NOT gate, the way it works is basically it takes one input only, okay, and it flips it around. That's it. So if you have a 1, it gives out a 0. If you have a 0, it gives out a 1. This also means that, actually, let me make room for this one. This also means that the NAND gate and the NOR gate were actually OR gate attached with the NOT gate, and the NAND gate was an AND gate attached with the NOT gate. Okay, so this is how the NOT gate works. Again, mathematically the way you would represent it is basically just use NOT A, okay, or the more compact way would be A bar or A dash. Okay, again, these are two different ways of representing the same thing. All right, the last gate we have is called the sixth gate that we have is called the XOR gate or XOR gate. This is the drawing of it, and basically the way this one works is basically it gives out 1, gives out 1 when both inputs are different. Okay, when both inputs are different. So where do we see the two inputs being different? In this row and in this row, right? So it's going to have a 1 in both these cases, otherwise it will give out a 0 when signals are same. All right, I'm going to represent it mathematically in a simple manner for the sake of your syllabus. Otherwise there's a more more complicated way of representing the XOR gate mathematically, but for now I'll just keep it very simple. I'll just say A XOR B. All right, this is how you would represent it mathematically over here. All right, so that was our introduction. These are the 6 gates that we have. I've shown you the tables, so ideally you should know how these what relation do these gates have for their input to output, right? So for what input what output should you get, so you should ideally just memorize it to be able to do the questions. Okay, remember that NOT gate just flips out the input, so whatever input it gets, it just flips it around and give it you the exact opposite output. All right, so that's it from the introduction. In the next video we will be looking at some circuits.